Hello, good people. How are you? Welcome back to Med Zone African Motives. We are still at it. We are still doing our revisions for our November examinations. We are on our preparations. So I've brought you another question paper, which is from Northwest Provincial Government. It was written as a provincial assessment for November 2024. It was a physics paper for grade 10. And this paper was supposed to be written in 2 hours. It was out of 100 marks. So let's use this question paper to also add on our revisions, to add on our exposure on questions, to add on our knowledge. So from this question paper, as we all know, we would be having multiple choice questions, and then we'll also have another section, which is open-ended questions, where you get to answer and write your answers as fully as you can. You are not limited to any number of words or else any options. You just get to write what you think, what you know, and what you understand in terms of the concepts that will be asked. So given that now, let's begin with our multiple choice questions. From our multiple choice questions, we are always given four options, and out of four possible options, we only have got one correct answer. So what we need to do is to choose the most accurate answer out of the four given answers. Now, let's see question number 1.1. It was actually saying the number of wave pulses per second is called. What is the number of wave pulses per second? So we know that frequency is the one that is defined as the number of wave pulses that are passing per every what? Per every second. So our answer was going to be C. Now let's go to 1.2. It is saying consider the two diagrams that are given below, which is diagram A, where we have got a certain pulse that is moving to your right with an amplitude of 30 centimeters, and then another pulse that is also moving to the left, which is also having an amplitude of what? Of 10 centimeters, and they are all in the positive what? Direction, mean to say they are all having crests. Now they're saying when the two pulses in the diagram meet at point X, the type of interference and the resultant amplitude of the distance will be what? We know that as long as two pulses meet at a certain point and they all have two crests, or else they have positive amplitude, they are going to actually have what we call constructive interference. So what is going to occur or happen at point X is what we refer to as what? Constructive interference. Where we are saying constructive interference is when two pulses meet and they have an increased amplitude, meaning to say from the one that is having the highest amplitude, we will now have a sum of these two amplitude giving you a greater amplitude from the what? From the maximum that you're having. But a destructive interference is when we have a decreased amplitude, meaning to say the resulting sum would be less than the maximum that we're having initially. So here you can see that if these two meet, they would have what? They would have an amplitude that is equal to 30 plus 10. That is going to be equal to what? 40 centimeters, because they are both in the positive direction. So when they meet, what is going to happen is they are going to have something like this, where we are saying we have added two of these to give us this this sum. So here we were going to have what? Constructive interference and an amplitude of what? 40 centimeters. So our answer there was going to be 1.2. For 1.2, it was going to be C. Now let's go to 1.3. A certain electromagnetic wave has 4.97 times 10 to power 10 to power negative 14 joules of energy. The frequency of the wave is. So we know that the energy of a wave is given by what? By h, which is the Planck's constant, times the frequency of the wave, which is just hf. Now, if we know the energy of the wave, which is 4.97 times 10 to the power negative 14 joules, and then they want us to find the frequency, we just have to divide throughout by the Planck's constant. And we know that the Planck's constant H is given by 6.63 times 10 power negative what? 34. So we are just going to divide that by 6.63 to the power negative 6.63 times 10 power negative 34. And what is it that we get? So that is what we want to see now. So if I say 4.97 times 10 to the power negative 14 divided by 6.63 times 10 to the power negative 34, I'm going to get an answer of 7.496 times 10 to the power 19. 7.496 times 10 to the power 19. That is almost approximately equal to 7.5. So my answer was 7.496 times 10 to the power what? Times 10 to the power 19. And that gives me what? That gives me my answer to be B there. So my answer was going to be B. So now let's go to 1.3, 1.4. So now 1.4 is now saying that, just a moment. Uh, in the following circuit, the light bulbs are identical. In the following circuit, the light bulbs are identical. Which switches must be closed for bulb A only to light up? Which switches must be closed for bulb A only to light up? So we can see that if we close switch 1, our current would actually get to what? To pass through all of these two bulbs. And then if we now get to close switch S3, you would see that the current would actually get to pass through to bulb B only, because we are saying that this switch will be open. Now, when we want switch A to actually get to what? To light up, we need to close this switch. So when we close that switch, current will not pass through B because switch 3 will be open. So we only need to close switch 1 and switch 2. So our answer there was going to be equal to what? To B. Now let's go to 1.5. They're saying the straight line difference in position, the straight line difference in position in space is called what? So here they're just talking about what? Change in position in a straight line. This is what we refer to as displacement. Displacement is the change in position in space in a straight line. Then consider the vector diagram given below, where we have got A, and then we have got C, and we have got B. Now they're saying, which one of the following correctly describe the relationship between vectors A, B, and C? Vectors A, B, and C. So you would see that if I'm to add vector A, and then I would add with vector B, this seems more like I'm saying I've got positive A and I've got negative B. They are going to give me what? They are going to give me C, because C is a positive. Because A is greater in magnitude, that is actually represented by the what? By this length. Greater than what? So the magnitude of A is greater than the magnitude of B. That is represented by the length. So these vectors are simply representing what? They are simply representing A plus B to be equal to C. That is what they are representing. And also from our vector diagrams, we know that we can either use tail to tail or else head to tail. So if we use head to tail method, we are saying that this is the tail of vector A, this is the head of vector A, and this is the tail of vector B, and this is head of vector B. So to find the resultant, we draw our resultant from the tail of our first to the head of our what? Of our last. That is what we refer to as what? As tail to head method. So you can see that we are coming from the tail of our first to the head of our last. So our answer there is to say that we have got A plus B being equal to C. So our answer was going to be A. Now let's go to 1.7. We are saying the kinetic energy of a moving body will increase the most if its dash. So if we want to increase the kinetic energy, we know that kinetic energy is given by half mv squared. So are we going to double our velocity, or else are we going to double the mass? Are we going to half the velocity, or else are we going to half the mass? So these two are already out. If we want to increase our kinetic energy, we need to increase these two. But which one will give the highest, or else the biggest kinetic energy in between this one? Which one will give the largest kinetic energy? It's when you actually get to double the velocity. Because if you double the mass, we are going to have 2 times half m v squared. That is simply equal to what? 2mv squared. But if I double the velocity now, you would have what? Half m 2v bracket squared. That is 2 squared, that is before. So it will be 4 bracket half m v squared. That is simply equal to what? To 2mv squared. So you can see that this is greater than that. So you need to double the velocity. So if you want to increase the kinetic energy of a moving body, you have to increase the what? The velocity. And also from the logic of it, if the body is already moving, all we need to increase is the what? Is the speed, because the mass of a moving body will not change. Or else, if you are to increase its mass, you might actually get to what? To decrease its what? Its acceleration. That would also decrease our what? Our velocity there. So you need to double its what? Its velocity from just logical thinking. Now let's go to what? Question number 2. The diagram below represents a transverse wave produced by a source. This is a transverse wave. And then they are saying define the term transverse wave. So we know that a transverse wave, this is a wave where the particles of this wave, they get to vibrate within the medium, or else you can actually come and say 2.1. A transverse wave is a wave, or else is a type of wave where the particles of the medium in which the wave is moving in, or else in which the wave is actually in what? In motion. They vibrate perpendicular to the direction of motion of the wave, to the direction of motion of the wave. So for you to be able to identify what we refer to as a transverse wave, you need to have particles in your medium. Let's say this is your medium, vibrating up and down, whilst your wave is moving in a what? In a horizontal what? In a horizontal motion. So you would actually get to see that your wave particles will be going up and down, whilst the wave is propagating what? In a horizontal direction. That is what we refer to as a transverse wave. You need to have, this is the type of wave where the particles within a medium in which the wave is propagating, they will get to move perpendicular to the direction of what? Of the wave itself. That is what we refer to as the transverse wave. Now write down the amplitude in meters of the wave. The amplitude is the maximum displacement of the particles. So the maximum displacement here is represented by the peak of this crest or of this troughs. So the peak here corresponds to 40 centimeters, and they say they want the what? The amplitude in meters. So you would say 40 centimeters divided by 100 centimeters. That is equal to what? 0.4 meters. That becomes the amplitude there. So the amplitude is just the what? The maximum displacement of the what? Of the wave particles. Now, determine the period of this wave. The period of this wave, this is the time taken to complete one complete wave. So the wave started here. If it actually gets to complete a cycle, it will actually get to what? To come back to where it started. Or else you would look at the what? at one crest to another crest. So the time taken to move from one crest to another crest, that is what we call a what? A period. So you would say the time taken to move from what? From one point in phase to another point in phase. So now we can use from 8 to 16. So from 8 seconds to 16 seconds. So the period T would be 16 minus what? Minus 8. That becomes what? 8 seconds. That is how you would have determined that. Or else you would have started from 0 here, which is where it started at peak, and then it also ended at peak. That is also 8 seconds. So we are just saying that the total time taken to complete one wave or else one pulse. Now they're saying if the distance d on the diagram is 0.9 what meters. So we need to now look at the distance d. They are now saying what is the name of the physical distance given to d. We know that the distance that is taken to complete one wave is referred to as the what? As its wavelength. So this is the what? The wavelength. Or else the distance in between two consecutive points in phase is what we call the what? The wavelength. So d represents the distance between two troughs. It is a distance between what? Two troughs. Or else a distance between two crests is what we refer to as the what? As the wavelength. Now calculate the speed of the complete wave as shown in the diagram. So the speed now, we know that the speed of a wave is given by what? By f lambda, where we are saying frequency times lambda. Now, we now need to calculate the frequency because we know now the what? The wavelength, which is lambda. Frequency can also be given as 1 over t, which is 1 over its period. So it is 1 over 8 seconds. So for my frequency here, I would come and say 1 over 8 times what is this distance that is covered. So you would come and say the distance that is covered, it is what? From here to there, they said it's 0.9 meters. So I would multiply by 0.9 meters. What becomes my speed then? What becomes my what? My speed. So my speed there, I would actually get to say 1 divided by 8, it's 0.125 times 0.9. That becomes 0.1125 meters per what? Per second. That becomes 0.1125 meters per second. 0.1125 meters per second. But in most cases, our answers would have been said we have to round them in what? Unto 3 decimal places, unless stated. So you would come and say 0.113 meters per second. So the most important thing there is how you find frequency. It is given by 1 over the time period, where the time period was what? Was 8 seconds. So I would have 1 over 8. And then the speed from the wave equation, it is given by what? By v is equals to f lambda, where v is the speed and f is the frequency and lambda is the what? Is the wavelength. Now let's see 2.5. Now they're saying the following sound wave produced by a turning fork is observed on an oscilloscope. This is the sound wave. A few more notes are played on different turning forks and the patterns below are observed. So we have got pattern A, B, and C. Identify the sound wave as either transverse or longitudinal. So we know that sound wave, its particles, or else the particles of the medium, they move parallel to the direction of the wave. So we call a sound wave what? Longitudinal wave. So sound waves are known as what? As longitudinal waves. Sound waves are known as longitudinal waves. Why? Because the particles within the medium, they propagate parallel to the movement of the what? Of the wave. Parallel to the direction of the wave, or else direction of motion of the what? Of the wave. So that's why we call it them what? Longitudinal wave. They've got what we call rarefractions and compressions. Now we are saying which one of the above patterns A, B, or C represents a louder note than the original note. So we know that when it comes to sound wave, pitch, we have something that we call pitch, the one that we either say it is of higher pitch or else it is of what? Of lower pitch. This is in relation to what we refer to as what? As frequency. So the higher the pitch, the higher the pitch, the higher the frequency. If we have got higher or high pitch, it means that we have got high frequency. And then when it comes to loudness or softness, the louder the what? The sound, the greater the amplitude. So we now get to say loudness is related to what? To amplitude. So the greater the amplitude, the greater the amplitude, the louder the noise, the greater the amplitude, the louder the noise, the louder the noise. So you need to know those two different properties. That we have got what? We have got frequency that is in relation to pitch, and then we have got amplitude that is related to what? To loudness. So from what was asked here, you would have just said that which one of the above patterns A, B, or C represents louder? Which pattern has got the highest amplitude? We can see that pattern B has got the highest what? Amplitude. This is the amplitude. The one that has got what? The greatest peaks. So B has got the what? This has got the louder note. This has got the louder note. And then this has got a what? A softer note. This has got a softer note. And then when it comes to a high pitch or soft pitch, the one with the high frequency is the one that would be related to high frequency, or else low pitch or high pitch. Now, they'll say, give a reason for your answer. You would say B has a higher amplitude. You say B has a higher amplitude. So they're just testing you if you understand what determines the loudness of the noise, or else the what? The softness of the noise. The amplitude determines that. So just for the sake of many others, let me just get to write a few notes aside so that people would actually get to what? To follow through. So we are saying that we have something that we refer to as what? As pitch and loudness. We have got pitch and we have got what? Loudness. So we are saying that pitch is related to what? To frequency. And we are saying that loudness of the sound is related to what? To amplitude. So amplitude determines what? How loud a noise is. So you would say greater amplitude, or else the higher amplitude, the greater amplitude, the greater the amplitude, the louder the noise. And then the lower the amplitude, or the smaller the amplitude, the amplitude, the softer the note. Now, when it comes to pitch, the higher the frequency, we would need to know that the higher the frequency, the higher the pitch. This is the property that we use when it comes to what? When it comes to Doppler effect. So we say that the higher the frequency, the higher the pitch. That is how you differentiate between the characteristics of what? Of your sound wave. So that is what, those are the notes that you are supposed to use here when you are answering these questions. Now, they are saying above which frequency is a sound wave classified as ultrasonic. So we know that for sound waves that are greater than what? 20,000 hertz, or else that are greater than 20 kilohertz. That is what we call ultrasound. And now they're saying, name one use of ultrasound in the medical treatment of patients. We know that we use ultrasound, one, for example, for actually monitoring the fetus or else the body with the monitoring the fetus. What do we mean by that? We are monitoring the what? The baby in the mother's womb. Monitoring the baby in the mother's womb. So what we call a fetus is the baby in the mother's womb. In the womb. So when you hear ladies saying that we are going for a checkup or else for a scan, what they're actually going there is actually going to be scanned using ultrasound. So at some point in time, we use ultrasound for monitoring the what? The fetus. That's why it's called sonic scanning. Sonic comes from ultrasound. And then we also use ultrasound for what? For checking blood flow. We also use ultrasound for checking blood flow. If the blood flow is flowing in a what? In the rightful direction, let's say for even the baby in the mother's womb, is the blood flow of the baby going in the rightful direction? And also to actually get to determine the blood flow within even an adult. So we use ultrasound for monitoring the fetus or else for what? For blood flow, to check the blood flow within what? Within patients. So those are just examples of what we use ultrasound for. Now, the electromagnetic spectrum includes, amongst others, we've got radio waves, the ones that makes your stereo FMs, the ones that helps us to have Wi-Fi at home. And then we have got ultraviolet, the one that we see that is actually what? That is used maybe for cleaning, like for example, for your water treatment. For those who know water treatment, we can use what? Ultraviolet light. And also for sterilization. For sterilization, we can use what? Ultraviolet. And then we've got gamma rays. These are the most deadliest waves that we will never wish to ever encounter. These are the ones that causes cancer. They cause a lot of things. So these are the rays that we never wish to ever come across. They've got the highest energy. And then we've got visible light, the one that we use for determining color, the one that we use daily to just get to have visuals. And then we have got what we call X-rays, the ones that we use for scanning our bones for those who would have fractured or else having broken bones. Now they are saying, how are electromagnetic waves generated? We know that electromagnetic waves are generated by accelerating charges. We know that charges are always in constant motion. They are always moving and they are always vibrating up and down, oscillating. Once you are able to accelerate those oscillations or else that movement of charge, then you can be able to what? To produce what you call what? Electromagnetic waves. And now they are saying, explain what is meant by the dual nature of electromagnetic radiation. We know that electromagnetic radiation can either exist as a particle or else as a wave. As a particle, they carry what? Energy. And then as a wave, they have got wavelength, they've got frequency. That is what we refer to as the dual nature of electromagnetic waves. So let me just get you right down here. So for 3.1, we have already said that for you to produce electromagnetic waves, you just need to what? To accelerate charge by accelerating what? Charges, or else accelerating electric charges. And then for 3.2 now, this is where they are saying, explain what is meant by the dual nature of what? Of electromagnetic waves. This is a phenomenon. This is a phenomenon where we describe electromagnetic waves as either particles which carry photons of energy, which carry photons of energy, or waves which have a wavelength or else frequency. Wavelength or else what? Frequency. So the phenomena in which we end up describing electromagnetic waves as either particles which carry photons of energy as well described or else well invented by what? By say by what? By Einstein. We know that Einstein got so famous with what? With the explanation of what? Of his photoelectric effect. He was explaining that if you take electromagnetic waves or else light, it behaves as both particles when it carries photons of energy or else as waves. So as particles, electromagnetic waves, they've got energy that we describe as what? As h times f, where we are saying h is Planck's constant and f is the frequency. And then as waves, these electromagnetic waves can be best described by what? By the relationship between the speed of the wave times the frequency and its wavelength. So this is the wave nature, and then this is the particle nature. So I'm sure you now agree that electromagnetic wave, they exhibit a dual what? A dual nature, either the particle nature or else the wave nature. That is what we mean by what? By the phenomenon where electromagnetic waves, they exist in a dual nature or else they exhibit what? A dual nature. From the information above, name the type of electromagnetic radiation that is used in hospitals to identify broken bones. This is what I was explaining on these. So, amongst radio waves, ultraviolet light, gamma rays, visible light, and X-rays, which ones are used in hospitals to identify broken bones? We all know that these ones are what? X-rays. Why? Because we have heard people say that when they've broken their bones or else they've fractured their bones, they will tell you that I'm going to an X-ray. Why? Because we want to identify the broken bones using the what? The type of electromagnetic waves called X-rays. And then which one is used in our Wi-Fi or wireless fidelity? These are what we refer to as what? Radio waves. These are what we refer to as radio waves, as I have explained earlier. They help us to get our stereos on. They help us to have what we call Wi-Fi, which is wireless fidelity. So for those who didn't know what Wi-Fi means, at least now you know. And then we now have which of the electromagnetic radiation has the highest energy. We say that these are the gamma rays. The most dangerous of all are the gamma rays. Those are the ones that are carrying what? The highest energy. They can ionize anything. They can ionize anything. That's why they are classified as the most what? Dangerous. That's why they would be able to cause cancerous effect. That's why they would be able to destroy anything because they can ionize anything. So they are called what? Gamma rays. You never wish to come across these. By any means, if there is a leak of gamma rays, try to fly if you can fly, because even the way they move, their frequency is the highest. After we've said that, now let's try to see 3.4. Now we are saying calculate the energy of a photon of microwaves with a wavelength of what? 2.1 times 10 to the power minus 2 meters. We want to calculate the what? The energy of the photon. So we said the energy of a photon is given by what? By h times f. But now we are not given frequency. But what do we know about frequency? We know that if we are given the speed, we can be able to calculate what? Frequency. So we usually take electromagnetic spectrum to fall under the what? The speed of light. So we usually use this V as c, which is the speed of light, 3 times 10 to the power 8 meters per second. So we already know the speed of light. So whenever we need to calculate the frequency of electromagnetic waves, we just need to know what? We just need to know the wavelength as well as we know the what? The speed of light. So here this can actually get to translate to say, if I have got V being equal to, if I've got C, let me use C, the speed of light. My speed of light being equal to frequency times my wavelength lambda. For me to find frequency, I would make it the subject, it would be C over lambda being equal to frequency. So wherever I've got this frequency, I'll substitute with C over lambda. So on my energy of a photon, I'll come and say H times C over lambda. That is the equation that we have. And we usually find this equation on our information sheet or our data sheet. And we know that H is 6.63 times 10 to the power negative what? 34 times the speed of light that I've just given you here. So just allow me to create space so that I can add that. So the speed of light there, we said it's what? It's 3 times 10 to the power 8 meters per second divided by, they've given us the wavelength, which is 2.1 times 10 to the power negative 2. Now let's punch in our calculators. 6.63 times 10 to the power negative 24 times 3 times 10 to the power 8. And then we have to divide by what? 2.1 times 10 to the power negative 2. That gives us 9.47. The answer is 9.47 times 10 to the power negative 14 hertz. So that was the frequency that we were supposed to find there. 9.47 times 10 to the power negative what? Times 10 to the power negative 14 hertz. That is the what? Sorry. Now I'm now saying hertz. It's supposed to be joules because we are calculating what? Energy. Pardon me there. It's supposed to be joules. So joules. Then thereafter, we then get to go to what? 3 point. We now need to go to 4.1. 4.1 is saying if the charge on sphere D was negative 2 coulombs before the sphere is touched, calculate the initial charge on sphere E. Now, this is the information that you are given about these diagrams. The diagram below shows two small identical spheres, D and E, on an insulated stand. The spheres are brought together to touch and then separated. After touching and separating, the charge on sphere D and E is plus 5 nanocoulombs. So after touching and separating, this is where we now have got these charges. Now they're saying if the charge on sphere D initially was negative 2 nanocoulombs, calculate the initial charge on sphere E. So we know that our final charge, or else our final average charge, is given by what? By the initial charge of D plus the initial charge of E divided by 2. We sum and divide by 2 after separation. So we are saying that after separation, we are having what? Positive 5 nanocoulombs. And then initially D was having negative 2 nanocoulombs. Now we are looking for charge of what? Of E. And then we divide by 2. So I can multiply by 2 this side, and then it will be 10 nanocoulombs equal to negative 2 nanocoulombs plus charge of E. Thereafter, I will just need to make this the subject. So let me just get to use a bigger space for this so that everything that follows, I will just get to use that space to calculate everything that follows. So we are just saying initially we were having our charge of D being equal to negative what? 2 nanocoulombs. That was the initial charge of D. And then the final charge of D, it's now what? Equal to positive 5 nanocoulombs. So we are looking for the initial charge of E. So what you are going to do is the average final charge. Let's get to say the average final charge of these two, which is just Q final average, is given by initial of D plus initial of E divided by 2. So substituting there, I would have negative 2. I will just keep nanocoulombs, charge of E initially, over 2. And then I'll take positive 5 nanocoulombs. Mind you, I'm keeping nanocoulombs because they are all in the same units. That's the reason why I'm keeping this. And so otherwise, I'll come and say negative 2 times 10 to the power negative 9, which is the same thing that I'll do this side. So since they're in the same units, I'll just keep them like that. It's more like we are using centimeters and centimeters. There is no need of converting to meters. So now I'll now need to multiply by 2 throughout. So now I would come and multiply by 2 this side, multiply by 2 this side. These two would cancel out, and then I'll now later have what? If I multiply I would have this one would be just negative 2 nanocoulombs plus initial charge of Q. Then this side I would be having 10 nanocoulombs. Now I now need to make this the subject, so I would transpose negative 2 to that other side. So it becomes 10 nanocoulombs plus 2 nanocoulombs. So my charge of E initially, it was actually what? 12 nanocoulombs. That was my initial charge of what? That was my initial charge of E, 12 nanocoulombs. That is the same unit that I'm given there. So to me, it was not necessary to convert to 12 times 10 to the power negative what? 9. Because we all know that that is what? So here you would say Q of E initially, you can leave it as 12 times 10 to the power 9 coulombs, which just means 12 nanocoulombs. Is the same thing. Now, calculate the number of electrons transferred when the sphere is touched. So the number of electrons that would be transferred now, we now need to know how much charge difference do we have. So we can either take for D or for E. Let's just go for D, the one that is given. So we know that the initial charge of D, is negative 2 nanocoulombs, and then the final charge of D is now equal to positive 5 nanocoulombs. What is the difference? So the difference in our charge there is going to be what? The difference in our charge in D, it is going to be equal to final minus initial. So we are going to say positive 5 nanocoulombs minus 2 nanocoulombs. That is going to give you 7 nanocoulombs. So we can see that the difference becomes 7 times 10 to the power negative 9 coulombs. That is what we have as our difference. Now, how do we calculate the number of electrons transferred? We actually get to say we have got a formulation which says the number of electrons are equal to change in the charge divided by the what? By the charge of an electron. Of which, what is the charge of an electron? We need to know the charge of an electron, and we know that the charge of an electron is given by what? 1.6. So this is equal to 1.6 times 10 to the power negative what? To the power negative 19. That is what we know. Coulombs. So we would come here and say we have got 7 times 10 to the power negative 9 coulombs divided by 1.6 times 10 to the power negative 19 coulombs. I just took the magnitude there, so that here my number of electrons, I would simply come and say 7 times 10 to the power negative 9 divided by 1.6 times 10 to the power negative 19. So the number of electrons were going to be equal to 4.375 times 10 to the power 10 electrons. So these are the number of electrons that have been transferred. Now let's see our next question. So our next question comes to say, were the electrons transferred from D to E or from E to D during contact? So now we are saying, how can we be able to determine that? We look at the initial charge of D and we look at the final charge of D. That is what we do there. You look at the initial charge of D and the final charge of D. And you also look at the what? Initial charge of E. And then you look at the final charge of E. The one that becomes, that is coming from a negative to a positive is the one that is transferring electrons. When you lose something that is negative, you become positive. So the one that is moving from a negative to a positive, or from a lesser positive to a what? To a positive. That is what we determine with. So our determination there would actually get to say the initial charge of D was what? Was negative 2 nanocoulombs. The final charge of D was positive 5 nanocoulombs. So D moved from a negative to a positive. It simply means that it lost some negatives for it to become positive. And we know that electrons, they carry a negative charge. So the one that lost electrons is the one that lost negative charges to become positive. And you see that initially E was 12 nanocoulombs, a positive 12. Now it is just a positive 5 nanocoulombs. It lost some positives, so it has gained some negatives, so as to balance the lost what? Positives. So that is how you determine. So the electrons were transferred from what? From D to E. So you would come and say the electrons were transferred from what? From D to T to E. So you would say electron transfer was from D to E. Why? Because D was a negative, is now a positive. So it has lost somewhat, some negatives, which represents electrons. Now let's go to question number 5. We have been given a circuit diagram below, and they're saying that the second diagram below shows 3 resistors which are connected to a battery, which is having those terminals. The voltmeter over the 4 ohm resistor is 12 volts as shown. Voltmeter V1 and ammeter A1 are connected as shown in the diagram. So voltmeter V1, we will measure the EMF within the battery when there is no current flowing, and then it will now measure external voltage whenever there is current flowing. The resistance of the battery, ammeter, and connecting wires can be ignored. That is what they're telling us. So we only need to look into the resistance of the what? The external circuit. Now, they are saying define potential difference. Potential difference is defined as the energy transferred per unit charge. The energy transferred per unit what? Charge. That is what we refer to as what? As potential difference. So 5.1, we are saying that potential difference is the energy transferred per unit charge. So the energy that is transferred to just move 1 unit of charge is what we call potential difference. And that is the drive of our electric charge within our circuits, that energy. Now they're saying calculate the total resistance of the circuit given this circuit. Now you would see that here I've got 4 ohm that is connected to a parallel circuit that is having 2 ohm and 2 ohm. So we need to calculate the resistance of this parallel circuit, which we know to say that it is what? Product divided by what? By sum. Whenever you are given 2 resistors in series, 2 resistors in parallel, you just have to make product over sum. Now, resistance in parallel, the product is what? 2 times 2 divided by what? 2 plus 2. That is product over sum. That gives you 4 over 4, and that is equivalent to 1 ohm. And then some, they will say, we know that resistance in parallel is calculated by saying 1 over Rp is equals to 1 over R1 plus 1 over R2. It's just the same. It's just that here we are now just using the shortcut of the end result that will come from that. But however, we would have just said, therefore, this is equal to 1 over 2 plus 1 over 2. Now we need to find the common denominator, which is just what? Which can just be 2, or else which can be just 2 times 2, which is 4. Let me use 2 times 2, which is just what? 4. 4 like that. And then I'll say 2 into 2, it's 2 times 1, plus 2 into 4, it becomes what? 2 times 1. Then this would become equal to what? To 4 over 4, which is equal to 1 over Rp. And then now I would simply say that Rp, I would interchange. I would actually come and interchange here. Interchanging, I would have 4 over 4. It's still the same, which is going to give me 1 ohm. So that is how you would have calculated the resistance in parallel here. Now, I would add with this resistance in series so that I have the total resistance. So my total resistance there, R total, would be the what? The 4 ohm resistor plus the resistance in parallel, which is just 4 plus 1. That is equivalent to what? To 5 ohms. That is how you would have just calculated your what? Your total resistance there. Now they are saying calculate the amount of charge that flows through an ammeter A1 in 120 seconds. So now the ammeter A1, you can see that it is measuring the what? The total current. Let me just get to rub here. You can see that the ammeter A1 is measuring the what? The total current. So this is measuring the total current. And what is our total current here? We can simply see that we can measure the current that is passing through here. I, after that 4 ohm, is the same current that will also come here, because it will branch here and then later regroup and come back there. So this is the same. Or else I would say 1.5 m plus 1.5 m is equal to the total current that is passing through there, which is just equal to what? 1.5 plus 1.5, which is equals to 3 amps. We know that current in a parallel circuit is summative. So the total current here would be equal to sum. So the current, that is the total current in our parallel circuit, would be equal to current 1 plus current 2, which is 1.5 plus 1.5. That gives you what? That gives you 3. That becomes the 3 amps that will also pass through and go and pass through at A1. So now, that is not what they asked. They asked the amount of charge that flows through ammeter A1. How do we calculate that amount of charge? We know that this is what we know. Let me just use this space. This is what we know. So I'll rub here. So we know that current is defined as the charge flowing through what? We know that current is equal to what? The total charge that is flowing per unit time. Total charge flowing per unit what? Time. Or else the rate of flow of charge. Let's just get to define it as the what? Rate of flow of charge, so that we will end up having total charge per unit time. Rate of flow of charge. So you would say your total charge per unit time, that is current. So this one would be what? It would be Q per unit what? Time. And then that would be equal to current. Our current is 3 amps. And then we are looking for charge in coulombs divided by the time in seconds. They said it is passing through A in 120 seconds. So our charge would be simply equal to what? 3 amps times 120 seconds. That will give you a charge in coulombs. So our charge was going to be equal to what? 3 times 1 point what? Our charge there was simply going to be equal to what? 3 times 120. 3 times 120. That is 360. That was going to be 360 coulombs. That is the total charge that you were supposed to find there. That was the total charge. So that is simply what you were supposed to do there. That is simply what you're supposed to do. To find charge, you would come back to the what? To the basics, to say what is defined as current. So our charge here there was going to be equal to what? Current times time. It was going to be equal to current times time, which is just 3 amps times 120 seconds. That is equals to 360 coulombs. That is what we did there. Now, what will become the reading on V1 if voltmeter uses 5,400 joules of energy and the same amount of current calculated in question 5.22 flows through it? So we are saying that now we want to find V1. We said initially our potential difference is what? Is measured as the what? Is the energy transferred per unit charge. So 5.23, now we are saying that V1 will now be equal to what? V1 will now be equal to what? It is just the total what? It is just the total voltage of the external circuit. Now, if it is the total voltage of the external circuit now, which can also be given as what? Which can also be given as the what? As the energy transferred, as we have defined it on top, divided per unit what? Charge. So the charge that we have just transferred there is what? It's 360 coulombs. And they are saying that the energy is 5,400 joules. Let's go back to the question so that you see where I'm taking my information. They said, calculate the reading on V1 if the voltmeter uses 5,400 joules of energy and the same amount of current calculated at the question 5.22. The same amount of current would actually get to what? It would actually get to pass through this amount of charge. That becomes 360 coulombs, and then that is the energy. So what we're going to do there is to use that formulation to say that also we know that, or else maybe I was just supposed to say that becomes V total there, so that it becomes the potential difference that is causing this charge to pass through. So if we say 5,400 divided by 360 there, you are going to get what? 150 volts. That is what you are supposed to do. That is energy transferred per unit charge. You know that there is a formulation that says V is equals to work done per unit what? Work done per unit charge. We know this formulation. So from this formulation, that's where we are saying this is our potential difference and this is our energy transferred, or else our work done. And then this becomes the charge transferred, or else the unit charge, or the charge passing through a point per unit time. So that is what we use there. Now going back and let's see our other questions. We now need to go back. Now they're saying a wire with negligent resistance is now connected from X to Y in the circuit. How will the reading on voltmeter V1 be affected? Let's go to our circuit and let's get to see if we connect the wire there. Now, connecting the wire, allow me to just get to wrap everything here. If we are to connect the wire, so I would want to say, let's say we connect a wire direct from X to Y. That's what we call short circuiting. What we have done here is we have eliminated this. We have eliminated this. We have eliminated this. We have eliminated what? That. By eliminating that now, we are saying that our current will simply flow from here, this is the positive terminal, to the 4 ohm and back to, so the only resistance that we have now, we now have a resistance of what? Of 4 ohms. That is now our final resistance. But initially, our total resistance initially, it was equal to what? It was equal to 5 ohms. So you see that now the resistance is decreased. So when resistance decreases, the current will simply what? Will simply get to increase, so as to balance the effect. So we are saying that what happens here if the resistance decreases? Let's say, for example, okay, fine, they did not actually get to mention anything to do with the change in current. We are still having that same current. They are now saying a wire with negligible resistance is now connected from X to Y in the second. How will the reading on voltmeter V1 be affected? So the voltmeter on V1 will decrease. Why? Because our external resistance decreases. So the current there remains the same. As the current there remains the same, it simply means that we are now banking on what? On our resistance to get our what? Our external voltage. So V external would be given by the current times R external. As we know that from potential difference, or else from EMF, from our total EMF would be having current R times the internal resistance. So now we are saying this is decreased. It simply means that IR external will decrease. That is what is being measured by V1. V1 is measuring external voltage when current is moving. It will only measure EMF when there is no current moving. So you would say that this would decrease. Why? Because our external resistance would decrease while the current remains the same. While the current remains the same. That is what we're just supposed to say there. Now let's see the following question. Now we are saying that In the Paris 2024 Olympics, Titan Smith won a gold medal in the 100-meter backstroke event when she completed this event in 65 seconds. Olympic swimming pools are 50 meters in length. So they are now saying, define the term average speed. The term average speed simply means the what? Total distance covered per unit time. Per unit time. The total distance that Titan covered per unit time becomes a average speed. Calculate the average speed that Titan swam to win the 100-meter backstroke. So you would say V average, you'd say V average is equals to what? Total distance divided by what? The time that she took. So now I would come here and say, what is our total distance? They said 100 meters. And what is our total time that she took for 100 meters? 65 seconds. Because they're saying in Paris 2024 Olympics, Titan Smith won a gold medal in the 100-meter backstroke event when she completed this event in 65 seconds. So the event was 100-meter long. So that becomes our what? Our distance. It was equal to 100 meters long. Our time that it took for this event was equal to 65 seconds. So if we want to calculate average speed, we would simply say 100 meters divided by what? 65 seconds. That is what we would simply say there. So the answer becomes what? 100 divided by 65. That becomes 1.538, which is just 1.6 meters per second. That is our average speed. That is how you calculate average speed. So those were the two questions for question number 6. Now let's go to question number 7. A text is traveling at a constant speed in a straight and level road where the speed limit is 60 kilometers per hour. So this guy is overspeeding. Define the term acceleration. Acceleration is the rate of change of displacement. Rate of change of velocity is the rate of change of velocity. You can say acceleration is equal to delta V over delta T. That is the rate of change of what? Of velocity. Convert 84 kilometers per hour to meters per second. Convert 84 kilometers per hour to what? To meters per second. So we know that the conversion unit that you use from kilometers per hour to meters per second, we divide 84 kilometers per hour by 3.6 kilometers per hour. Then that gives us meters per second. So if I say 84 divided by 3.6, that will give me what? 23.33 meters per second. And someone would say, but say that is not how we were taught. That is not how we were taught. Yes, I would understand. So I'm saying I have got 84 kilometers. I want to convert to meters. I have got 84 kilometers per what? Per 1 hour. So how many kilometers are there? How many meters are there in a kilometer? So you would say that there are 1,000 meters in what? In 1 kilometer, so that you can be able to cancel the kilometers. And then how many seconds are there in an hour, so that I can cancel out these hours? I have got what? 3,600 seconds. So I would cancel those. So I'm more like saying 84 times 1,000 divided by 3,600 meters per second. And then that will give me the same effect. That would be 84,000 divided by 3,600. If I do that, I would be left with 840 divided by 36, which is the same as 84 divided by 3.6. And it will give me what? If I punch in my calculator, it will also give me 23.33 meters per second. So that is how we came up with the factor to say just divide by 3.6 on the number of kilometers that you are given there. You would get the what? the same answer. So after we have said that, here we are divided by 3.6. Our 84 kilometers per hour was equivalent to 23.33 meters per second. A traffic officer starts his car from rest just as the text passes him. The traffic car accelerates uniformly at 2 meters per square second until it reaches a maximum velocity of 25 meters per second. Calculate the time that it will take the traffic car to reach its maximum velocity. Now, let's write down the information that you are given. That is 7.3. On 7.3, a traffic officer starts his car from rest. So the initial velocity of the car or the traffic car of the traffic cop is actually equal to what? 0 meters per second. And then the traffic car accelerates at what? The acceleration of the car, it is equal to 2 meters per square second until it reaches a maximum velocity of what? 25 meters per second. Final velocity of the car, it is 25 meters per second. Calculate the time that it takes the traffic car to reach its maximum velocity. We have got equations of motions which say Vf is equals to Vi plus acceleration times what? Times the time taken. So we are calculating this. So my final velocity is 25 meters per second, and then my initial velocity is 0. My acceleration is 2, and I'm looking for time. So I can simply divide throughout by 2, so that I would have what? My time taken there would be 25 divided by 2, that is 12.5 seconds. That is how you are going to calculate what? 7.3. Now they are saying determine by calculation which vehicle, the text or the traffic car, is ahead after t seconds has passed. So after this time, after 12.5 seconds, which car is ahead of the other? Which car is ahead of the other when we have moved a time of what? Of 12.5 seconds. Now, let's hear what is happening here. They said a traffic officer starts his car from rest just as the text passes him. So, as I had said earlier, this text was speeding, was overspeeding, because it was moving at 80 kilometers per hour when it was supposed to be moving at 60 kilometers per hour. So, when they pass through the traffic cop tries to catch after it because he is actually what? Speeding. He's breaking the law. So they want to know after a time of 12.5 seconds, which car would be ahead? Will it be the taxi? Will it be the traffic car? Which one would be ahead? So my initial velocity of the what? Of the taxi is 84 and my final is 84. It is moving at a constant speed of 84 kilometers per hour. But its main problem is that it actually moving at 84 kilometers per hour where it's supposed to be moving at what? At 60 kilometers per hour. That is the crime that taxi has committed. That's why we need to chase after him. So we need to know if we were to speed up until we reach 25 meters per second in our final velocity, will we be able to catch him? So you would come and say 7.4 initial of the taxi is what? 23.33 meters per second, and the final is also what? 23.33 meters per second. So now we would say what is the distance that was moved by the what? By the taxi. We know that we can use what? Average velocity times the time taken. So the average velocity is 23.33, or else we can say 23.33 plus 23.33 divided by 2 times the time taken. We said it's what? 12.5 seconds. 12.5 seconds. Because we know that average velocity is given by what? By final velocity plus initial velocity all over 2 times the time taken. So this is what I have just done here, to say its final plus its final divided by 2, its final plus its initial of the text. So the taxi, the distance that would have been moved by the taxi, if we do this, we are saying that it will be equal to what? It will be equal to 291.667 meters. That is the total distance moved by the what? By the taxi. Now, let's look at the distance moved by the traffic car. Now, initial of the what? Of the car is 0. Final of the car, it's what? It's equal to 15 meters per second. The acceleration is equal to what? 2 meters per square second. So we can use delta x is equal to what? VIT plus half AT squared. Someone would ask me, why didn't you use this one of average velocity? Why can't you use the one for average velocity? I can even use the one for average velocity to say that my average velocity there would be to say I would use delta x is equals to V average times delta t. My V average would be to say final plus initial, that is 15 plus 0 divided by 2. And then I would multiply by what? 12.5. You would see that the distance that would be moved by the traffic cop would be just what? 93.75 meters. What about if I use this equation? My initial is 0, so this one goes also to 0, plus half of 2 times 12.5 squared. That becomes what? 12.5 squared. 156.25 is still the same. So why I didn't use this, it does not give me a what? A clear picture of what happened, because my car is accelerating. So I cannot take the average. My car here is accelerating. I have got a car that is what? Accelerating. So if it is accelerating, its rate of change of velocity is significant. But if it is constant, the rate of change of velocity is insignificant. So you would find here that now I would say half of this times 12.5 squared, I would find 156.25 meters. So you would see that for this one, you would find the same answer even if you were to use the equations of motion to say, okay, fine. Let's say delta x is equals to VIT plus half AT squared. You would see the initial velocity is what? 23. You would come and say the initial velocity is actually 23.33 times the time taken 12.5 plus half. What is the acceleration at constant speed? You have got acceleration of z. So definitely this one will go to z. So I would be having 23.33 times 12.5. That gives you the same value that we found, which is 23.33 times 12.5. That is equal to what? 291.625 meters. So you can see that the taxi moved a longer distance. So what was the question there? So that we can be able to answer the question. We now know that the taxi moved the longer distance. They are saying, assume that the taxi maintains its constant speed determined by calculation which vehicle, the taxi or the traffic car, is ahead after t. You can see that the what? The taxi is ahead. Why? Because the taxi has moved the longer distance from what we have calculated. So that is what we were supposed to do there. Now, let's go to question number 8. A driver stops his car at the red traffic light. The graph of the car's velocity against time shows its motion from 8 seconds from the time the traffic light turns green. So now, they are now saying, let's hear the questions below here. So this is the graph from the time the traffic light turns green. This is how the car has moved. Now, the short time interval between the traffic light turning green for go and the driver responding to the signal is known as driver's reaction time. How long does it take the driver to respond to the traffic light changes? So it took from 0 to something like what? 0.8. It took him from 0 up until here. So it took him what? 0.8 seconds. It took him 0.8 seconds from 0 to 0.8 seconds. So it took him 0.8 seconds. And then now they're saying, determine the maximum speed of the car. The maximum speed of the car is given by that. You just get to read using the graph. What was the maximum speed there? So this box in terms of speed, it is representing what? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 boxes representing 5 meters per second. So if I say 5 divided by 10, so that each box represent what? 0.5 meters per second. So here I've got 11, I've got 12, 12.5. So here I've got 12.5 meters per second. So the maximum velocity there was just 12.5 seconds. How did I find it? I just read it from the graph, 12.5 meters per second. So you need to know how to calculate it from the scale and also how to plot. Now, use the graph only, no equations of motion, to calculate the average acceleration of the car. So the average acceleration of the car, you would use the gradient there. You would use the gradient because they said use the graph only. So a velocity time graph, it will give you acceleration through its gradient. The gradient of the acceleration time graph of the velocity time graph gives you what? Acceleration. So the gradient here, I will take the gradient there. So I'll take 2 points there. So this becomes my first point, that becomes my second point, or else that becomes my first point, that becomes my second point. So I would say the gradient, which is acceleration, is equal to delta y over delta x. That is to say y2 minus y1 over x2 minus x1. That is simply v2 minus v1 over time 2 minus time t1. And then now, what is my v2? Here it's 12.5. 12.5 minus what is my v1 here? It's 0. 0 divided by what is my time taken here? I can see that this is 5.8. 5.8 seconds minus what is my time taken here? 0.8. 0.8. So my gradient was just going to be 12.5 minus 0 divided by 5.8 minus 0.8. And then that was going to give me 2.5 meters per square second. So that is how you calculate acceleration from the velocity time graph without using the equations of motion. You just use the what? The gradient. Now 8.4, use the graph only, no equations of motion, to determine the displacement of the car over the 8 seconds. So from a velocity time graph, you use the area under the graph to find the displacement. You use the area under the graph. So let's look at our graph so that we can be able to determine our area. So on this graph, I will take the area that is actually under this part here, coming from this part. So this would be given by half base times height. And then I would add the area under that rectangle there. It will be given by length times its breadth. So now I would say, what is the base here? It is 5.8 minus what? 0.8. So it is just what? 5.8. If you say 5.8 minus 0.8, that is our what? Our base. So I would say this is 1. Let me just use this side. I'll use length times width so that I can differentiate between the two. So this side I will be using length times width. So here I've got my base being equal to what? To 5. So here I would come and use half of 5 times. What is my height from here to 12.5? It is just 12.5. And then what is my length here? My length can be this height. So it becomes what? It becomes 12.5 times my width, which is my breadth, becomes 8 minus what? 5.8. 8 minus 5.8, it will be 8 minus 5.8. That gives you 2.2 times 2.2. That is what I was just supposed to do there. And then I add. So let me go down there and show you how I would have calculated my area under the graph, I would come and say displacement delta x would be equal to what? To area A plus area B, where now area A is given by half base times height, and then area B it's now given by what? Length times width. Now filling in the details, it will be half of my base, it's 5.8 minus 0.8. That is my base times my height is just what? 12.5 plus my length, we said it's just 12.5 times my width, it becomes 8 minus 5.8. By doing that, I'm supposed to find an answer of saying 12.5 times 2.2. That gives me 27.5 there. What about this side? I would have 0.5 times. I have 5 times 12.5. So I would have 31.25 here, 31.25 meters. So if I add these two, I'm supposed to get 27.5. I'm supposed to get 58.75 meters. That is what is supposed to be my what? That is what is supposed to be my total displacement. So that is how you are going to calculate your displacement. Now let's look at question number what? Question number 9. Question number 9 is saying the graph below shows energy against position of a pendulum bulb, mass 50 grams, as it moves from A to B to C. So A to B and then to C. A resistance is negligible. If that is the case, our total mechanical energy would be conserved. Now they're saying energy against position for a pendulum bulb is given below. Okay, fine. Define gravitational potential energy. What is gravitational potential energy? We know that gravitational potential energy, this is the energy of an object due to its position. Energy of an object due to its position or what? Height. In reference to what? So, to some in reference to some gravitational what? In reference to some gravitational field relative to some point. Or else you can just get to say energy of a object due to its position or height, or else strain. Or you can say strain. That is gravitational potential energy. So gravitational potential energy would remove strain so that it becomes due to height, or else position due to height. So potential energy is where you would include just what? Strain as well. Determine the maximum potential energy of the bulb. Maximum potential energy of the bulb will be determined by the what? Maximum height there, or the maximum height there. So we can see that we have approximately what? We are coming from 0, because when it is here, this is where it has got what? Its maximum. Let me take you back to the pendulum. When it is at position A, this is where it has got its maximum gravitational potential energy. When it is now at B, that is where it will be having its maximum kinetic energy. And here, the potential energy would be equal to 0. And as well as at C, potential energy would be maximum. But here, kinetic energy at some point in time can be equal to 0 if it gets to point C and goes back. Now, if that is the case, we now know where our maximum potential energy would get on those 2 points. Now, let's go back to the diagram and see where you would represent A and C. A and C, we have here and there. So now we have got 0.20, and then from there we have got 1, 2, 3, 4, 5 boxes. So let's say each box will represent what? 0.4 minus 0.2. That is 0.2 divided by 5. So each box will represent 0.2 divided by 5. It will represent 0.04. It will represent what? 0.04. So here I have got what? 0.20, 0.24, 0.28, 0.32. So we can say 0.3 here. We can assume 0.30 joules. So here you can come and say maximum potential energy is what? 0.30 joules. From the graph, everything is taken from the graph. Calculate the maximum gain in height of the bulb. So the gain in height would say that we know that our gravitational potential energy is given by what? mgh. And this is our gravitational potential energy. And we know its mass, we know the gravitational acceleration. So I can come and say 9.3. I can come and say 9.3 0.30 is equal to mgh, where my mass, they said it's 50 grams, so it will be 50 divided by 1000 times my gravitational acceleration is 9.8, and then times my height. So this is the gain in height. Now I would divide throughout by this. So I would divide by what? If I divide 50 divided by 1000, it becomes 0.05. So this is 0.5. 0.05 times 9.8. If I do that, these two would cancel out. And then this side, I would also come and divide by what? 0.05 times 9.8. So that my gain in height now will now be equal to h gained. It would be 0.03. You are now saying 0.3 divided by 0.05 times 9.8. That will give you 0.612 meters. That is your gain in height. 0.621 meters. That is your gain in height. Now they're saying calculate the maximum speed of the bulb at position B. So what is happening here is at position B here, we are saying that since there is no air friction and whatsoever, our total mechanical energy is being conserved. That's one thing that we need to note. Our total mechanical energy is what? Total mechanical energy is conserved. If it is conserved, it means that it is constant throughout. So the total mechanical energy at point A should be equal to total mechanical energy at point B. So let's use that. Let's use that now to calculate our velocity at B. Now, I would come and say 9.4 here. 9.4, I would say total mechanical energy at point A should be equal to total mechanical energy at point B. Total mechanical energy at point B. Now, total mechanical energy at point A is potential energy at point A plus kinetic energy at point A. Now, total mechanical energy at point B is potential energy at point B plus kinetic energy at point B. We say that at point B, potential energy is equal to 0 because it is at the ground. So this would be simply equal to what? To kinetic energy. And kinetic energy is given by half mv squared at point B. Now, this is where you would be having your maximum kinetic energy. So that would be the maximum velocity there. If that is the case, this side, we said kinetic energy there would be 0 initially because it is just starting at rest. So we'd be left with this potential energy at A. And we have calculated it to be 0.30. If that is the case now, I'm now just substituting what I have and then get to C. So for me to find this or to make this the subject, I'll multiply throughout by 2 to be 2 times 0.30. And then I'll divide by the what? By the mass. And the mass is just 0.05. And then I would get my what? My maximum velocity there squared. And then I would root this side, I will root that side. So if I do that, I would see that my maximum velocity, which is at point B, would be given by what? I now need to say root of what? 2 times 0.30 later. So I was just supposed to have a bracket there. And then later divide by 0.05. So the velocity there, the total velocity there, you would have 3.464 meters per second. You would have 4.364 meters per second. That is your velocity there. 3.464 meters per second. Now let's hear our last and final question, what they are saying. State the law of conservation of mechanical energy in words. Let me just get to rub here and state that law here because we have already used this. So the total mechanical, the law of conservation of mechanical energy. The law of conservation of mechanical energy is just to say that the total mechanical energy is constant or else conserved whenever we've got a closed system. So you would say that in a closed system, you would come and say in a closed system, you would come and say in a closed system, comma, total mechanical energy is conserved. So in a closed system, total mechanical energy is conserved, which can be given by total mechanical energy at point A should be equal to total mechanical energy at point B. That is what we did there. We assumed that that system was closed by saying, assume that the air resistance is is negligible. That is the only force that would have acted upon that pendulum. So that was that, and that was our question paper, which was out of 100 marks. So thank you so much, guys, for being together. Let's meet once more in the next videos to come. So let's keep on practicing. Let's keep on working through our question papers. Let's keep on revising and preparing for our November exams. So we say more light and more winning. Thank you so much.